Hello guys, welcome to Photons, Einstein's photoelectric equation, and don't confuse it with Einstein's famous equation E equals to mc square. So here, let's use what we know. We know work function. Let's use its definition. The minimum amount of energy required to emit the electrons or knock out an electron from its orbit. So let's just say this is 5 joule, and if we have an energy of just 5 joule, then the electrons will just emit out of the orbit, right? So let's call that energy as E minimum because it's the minimum amount of energy, which is equals to 5. Now we know Max Planck's equation for energy, which is E equals to hf. Now here let's just call this E minimum energy as hf naught. So here f naught is known as the minimum frequency. So the minimum frequency of the radiation to just knock out an electron from its orbit, right? To just emit that electron, to eject that electron. It is also known as threshold frequency. So threshold frequency, right? And here let's use an energy E, which is greater than the minimum energy. So if we have that, then we have, let's say, 10 joule, and then this minimum energy is, let's say, 5 joule. So what that means is that the work function here will of 5 joule, let's say, will absorb some of that 5 joule from the 10 joule, and the rest of the energy will be transmitted as kinetic energy, right? So that means if we have 25 joules of energy of the upcoming photon from the electrons, sorry, of the radiation, then the work function will absorb 5 joule, and the rest will be converted into kinetic energy. So let's write this as a general term of equation, right? So here this is E minus the work function equals to rest converted to kinetic energy, which is hf minus phi equals to kinetic energy. Now as we said earlier that phi is equals to hf naught, so hf minus hf naught is equals to kinetic energy. And we all know the equation for kinetic energy, so therefore hf minus hf naught is equals to 1 by 2 mv square. This is in fact Einstein's photoelectric equation, but however we can further mathematically derive this in terms of wavelength and speed of light. So here let's say c is the speed of light and lambda is the wavelength associated with frequency, and lambda naught is the threshold wavelength associated with the uh, threshold frequency. Now please don't confuse by saying this is the minimum amount of wavelength, as you might get confused, because here frequency is directly proportional to wavelength. So that means they're inversely proportional. That means the less amount of frequency we have, the more amount of wavelength we have. That means the length of the wave of the photons will be larger. So in fact, the threshold wavelength is defined as the maximum length of the wave required to just eject an electron from an orbit. So instead of all that confusion, just say that this is threshold wavelength and this is threshold frequency. So here we know that C is equals to lambda f. So that means frequency is equals to C by lambda, and similarly f naught is equals to C by lambda naught. So let's put that in this equation. So we have h C lambda minus h C lambda naught equals to 1 by 2 mv square. So therefore we have h C common, 1 by lambda minus 1 by lambda naught is equals to 1 by 2 mv square. And you can see from this relation 1 by lambda minus 1 by lambda naught that here lambda must be shorter than lambda naught, right? Because here this will simplify to lambda naught minus lambda by lambda into lambda naught. and in order for this to stay positive, then that means lambda naught minus lambda must be positive, that is lambda must be smaller than lambda naught. So yes, that means that the threshold wavelength is the maximum length of the wave, that means the longest wave that can eject the electrons. So this is for Einstein's photoelectric equation. Now in the next video, I'll be doing Millikan's experiment to prove Einstein's photoelectric equation and also to calculate the value of h, that is Planck's constant. If you learn something new, please like and subscribe. Thank you.